Okay, let's start. Okay, so last time we studied about the vector equation. So given a linear system, okay, see. Yeah, so originally we considered this form of a linear system composed of multiple linear equations, but this equation can be viewed as a single vector equation by just treating each column in our augmented matrix. So in this augmented matrix, so we have the first column vector and the second column vector, and then we just multiply x1 times x2, x1 times the first vector plus x2 times the second vector, and then this linear combination of these two vectors should be the same as this constant vector that we are given on the right hand side of our linear system. Okay, and then we studied a really important notion of span. Okay, so span is defined as given a particular column vectors. Okay, so we are given a set of vectors, and then we consider all the possible linear combinations of these ingredient vectors. So we are given these input vectors or ingredient vectors, and then we just form this linear combination by just freely changing these values. So sometimes it can be 1, 0, and 0, and 1, 1, and 0, and 1, 2, 3, and so on. Okay, so by freely changing these linear combination coefficients, it can be viewed by collecting all these points by changing the linear combination coefficients. We can think of their collection of these linear combination vectors, and then in the case of having these two vectors, u and v in this case, so u and v are our two given vectors, and then we just freely stretch or shrink the length of these vectors by just multiplying a particular linear combination vectors. So when it is like 2u plus 1v, so here u and v are vectors, so these are these column vectors, right? And then it is corresponding to so this one is corresponding to u 2 times u, which is which has twice the length of the original vector, but with the same direction. And then this one is 1 times v, and thus the resulting point will be here, right? So we studied about this parallelogram, and then this vertex of our parallelogram is the resulting vector after adding these two vectors, right? So this one is corresponding to the point where we have 2, 1 or 2 and 1 as a linear combination coefficient, But what about like 1 and 2? It will be corresponding to here. And maybe 0 and 1, and it will be corresponding to here, right? And then what if we use -1 and -1, and then it actually reverses the vector direction, right? But still, yeah, we can form this parallelogram, and then collecting all these points, and then we can now see those points forms this straight plane, yeah, spanned or stretched by these two ingredient vectors. Okay, so this blue plane is called a span of these two vectors of u and v. Okay, so that is the notion of the span. And then in case we have just a single vector, okay, so this is still in three-dimensional space. So in this three-dimensional space, suppose we have some point or some vector like v as maybe 1, 1, 1. Okay, so it is the point in the three-dimensional space that has these coefficients of 1, 1, 1. And then we can also think of this span of v, which is our single given vector. And then in this case, yeah, we consider it's a linear combination. And then that linear combination is represented as C1 times V. And so V is like this three-dimensional vector. And we freely change this guy, okay? Like 0, in this case, it will be corresponding to just the origin. And then if it is 1, and then if it will be this point. And then if it is 2, and then it will be the vector that has the length of twice the original length. And then -1 will be corresponding to here. And so in this case, the span of this single vector will form this straight kind of line, right? So that is the notion of the span, okay? Okay, any questions so far? Okay, then let's now move to chapter 1.4, which is a matrix equation. Okay. So far we studied vector equation in the previous chapter. So now in this chapter we study the new term called a matrix equation. Okay, give me just 1 second. Okay, and so in this chapter, we will study the new form of an equation called a matrix equation. But let me just jump to a little bit more difficult part directly in this sub-chapter. So we first study this Theorem 4, which is about the existence of the solution. So let's recall or remember when our linear system has the solution or not. Okay. So previously, when thinking about the position of the pivots, okay, so again, the pivot is the leading entry or the first non-zero entry in each row, okay, but we consider, we first have to create or convert our matrix into echelon form, and then the first non-zero entry in each row will be called a pivot, right? And then in terms of these pivot positions, or in our echelon form, if we, so this is our echelon form of a matrix. So we have, suppose we have some kind of staircase like this. Yeah, and then in the last row, or in somewhere in our echelon form, if we see rows like all zeros, and then so in our echelon form, in some rows, if we find all zeros except for these non-zero entry in the last column, okay, in this case, we can see that we have no solution, and this last equation or last row is corresponding to like the 0 times x1 through 0 times x maybe n equals some non-zero values like 3. So in this case, we have no way to satisfy this, right? This was when this is when we have no solution at all, right? But now, because we studied the new notion of the span, let's think about this existence of solution in a slightly different perspective, okay? So, in general, whether we have a solution or not is dependent on the coefficient as well as the constant values on the right hand side, okay? So let me, if you remember the one example that I showed last time, so x1 times 2x2 equals -1, -1, or and 2x1 plus 4x2 is equal to maybe -2. In this case, do we have a solution or not? We have a solution, right? But what if I gave you like 2? In this case, we see we have no solution at all, right? So in general, suppose this left-hand side is fixed, okay? So we assume that the left part is all fixed, okay? And in that case, depending on these constant values on the right-hand side, okay, depending on the variable, depending on the values that we have on the right-hand side, sometimes we have a solution, but sometimes we will not have a solution, right? But what about this case of so do we have a solution here? Do we have a solution? Oops, the solution will be this guy, right? So we have a solution, right? Then let me change this guy into 0. Do we have a solution? We do, right? And then what about like -2 and 1? Yes, right? So in this case, regardless of what values we are given on the right-hand side, we can see that the solution always exists, right? So again, the point is, regardless of any values on the right-hand side that we are given, so we can see before, even before we see the particular values on the right-hand side, we can just say that this linear system should have a solution, right? So we consider this kind of case, okay? So we now study when this is the case. Okay. So again, the point is, before we see these values, we should be able to say that our linear system should always have a solution. Okay. And that is yeah. So in order to study when this is the case, we will just utilize the new notion that we studied, which is a span. 아, 스피커요?
혹시 마이크 안 되시나요?
이 마이크가 지금 뮤트가 있어요. 그렇죠? 이게 Give me 1 second.
저기 마이크 소리가 안 들어가서.
아, 네. 이거를 다시 해보죠. 이걸 테스트 좀 해보세요. 네. Okay. So again, we utilize the notion of a span in this case. Okay. So given a linear system, like, yeah, suppose we have a, what was it? Yeah, suppose we are given this kind of linear system. Okay, so in this case, we can see that this one can be viewed as a single vector equation, right? And so in that vector equation, it is, yeah, so the problem is now viewed as finding the suitable linear combination coefficient of an x1 and x2 in order to satisfy this vector. And geometrically, suppose this vector was something like this, and this vector was this vector. And then this 7.4, negative 3 was somewhere around here. And then, as we saw in the last lecture, we want to draw this parallelogram, right? So that the vertex of this parallelogram is exactly equal to the given B point or B vector. But yeah, in this case, we have to find the scales or the the scaling factor that has this vector length, right? So in this case, it is so V1 or A1 and A2. So it can be viewed as 0.5, and then this guy, the length of this vector is some values like this value, right? So the problem is to find these two linear combination coefficients, right? But the the necessary condition, I mean, at least in order to be able to represent this B point as the linear combination of the given vectors, okay, the necessary point is, the necessary condition is that this B vector should be inside of our span of these two vectors, right? Because this one is containing all the possible linear combination of these given two given vectors of an A1 and A2, right? And then in order to represent B as this linear combination of these given vectors, okay, and then at least this B should be inside of our span of these two vectors, right? Okay, so and then in this case, let's consider the three-dimensional space, which is actually the case in this example. So suppose we are given these two vectors, the first one and the second one, okay? And then we can imagine the span of these two vectors, and then if the B vector is outside of this span, and then we can see that the solution doesn't exist at all, right? But can we say that, okay, can we imagine that? Imagine the situation where we have always the solution regardless of this the position of this vector B. So let me give an example. So suppose we are instead of having these two vectors, suppose we are given like three vectors, and then the first vector and the second vector, and then up to these two vectors. The span of these two will be this plane, right? And then what if we add these third vectors? Okay, and then forming the parallelogram by using these three vectors. Okay, and then let's imagine all the possible linear combinations of these three vectors. So let's just think about the example where we use the linear combination coefficient as all ones, okay? And then in these given these three vectors, and then what will be the vertex or the resulting vectors of this linear combination coefficient? It will be somewhere around here, right? So it's a little hard to draw in this three-dimensional vectors, but so it is a little bit difficult. But this one is V1 and V2 and V3. So this is not in a two-dimensional space. So let's imagine that they are some vectors like this, okay? And then how can we compute this vector? So let's just form the linear combination of these first two vectors, okay? And then in this case, it will be the point of here, right? So it is just a parallelogram, vertex of this parallelogram by using these two vectors with the linear combination coefficient as 1, right? And then we now have this first vector, and then also we have a second vector as a V3, right? And then V3 has the length of 1, or it is multiplied by 1, right? So we just used its original length, and then we now form the new parallelogram by using these two vectors, right? So this is a resulting vector, and then this vector can be viewed as like so let me try to draw these three-dimensional parallelogram. So, or let me see if I can search for the proper figure. Okay, so I wanted to have this figure. Okay, so let me just H. Okay. So suppose this guy is V1, and this guy is V2, and this guy is V3. Okay, and then V1 and V2 will be this guy, right? This point, and then this guy plus V3, 1 times V3 will be the new forming the new parallelogram like this and this. Okay, so let me just draw this new parallelogram like this. Okay, so in this new parallelogram, the resulting vector is something like this. Okay, so it can be viewed as like three-dimensional parallelogram when adding these three vectors, and then that point, the resulting linear combination of these three vectors will be corresponding to this vertex in this three-dimensional parallelogram, right? And then what if we just change our linear combination coefficient associated with each vector, like maybe 1 and 1 and 2. So in this case, so we stretch out the V3, right? Yep. 언제부터 이랬죠? Okay, so let's think about this linear combinations of these three vectors. In that case, still, the length of the vertex of these parallelogram will change, but still this three-dimensional parallelogram kind of idea will exactly apply, right? So we now stretch out the length of this vector V3 twice, right? So we have like this vector. So suppose this one has the length, twice the length of the original vector. Okay, so in that case, our parallelogram, in this three-dimensional space will change, right? And thus the corresponding point will also change, right? Okay, so this is the linear combination of the three vectors. Okay, and then now let's think about the span of these three vectors in the three-dimensional space. So again, we are given these three vectors, okay? And then we now understood the linear combination of these by using the linear combination coefficient as 1 will be somewhere around here, right? And then let's just freely change these values, okay? And then collecting all the possible points by changing these linear combination coefficients. What will be the resulting set of all these points? So first of all, let's think about the span of these first two vectors, v1 and v2. Okay, and then in that case, it will just correspond to the linear combination. All the possible linear combinations by just setting the linear combination on this v3, right? So in that case, so we just ignore v3, and then it will be the plane spanned by v1 and v2, right? So it will be like a horizontal flat surface or plane, right? So that will be the all the possible points formed by this linear combination of v1 and v2. And then now we can adjust their height, right? By adding a little bit of, by starting to add a little bit of a v3, right? And then we initially had this horizontal kind of plane, right, as a collection of the points, right? And then if we add a little bit of a v3, right? Suppose we added like 0.1 v1, 0.1 times v3. So in that case, this plane will be, will be like placed in a little higher position, right? and a little high. Yeah, by changing this value, this plane will be a little higher and so on, right? Although the direction of this elevation or direction of increasing the height will be along this a little slanted direction, right? Not this straight vertical kind of direction, right? But still, this plane will be placed in a higher position and a higher position and so on. And then collecting all the points inside of these different the planes at a different height. Eventually, all the points spanned by these 3 points will be covering up the entire space in our 3-dimensional space. Is it correct? Is it right? So again, the point here is that in this 3-dimensional space, the span of these three different vectors, okay, will be actually the same as the entire space of R3. Okay, so basically, all the points in 3-dimensional space can be represented as a linear combination of these 3 given vectors. Okay. So what does that mean? What does that mean? Is it, in this case, is it possible that vector B on the right-hand side of our linear system, can it be outside of our span of these 3 vectors? It is impossible because our span is now the entire space of these 3-dimensional space, right? So there is no way for this vector B escape from the span of these 3 vectors. Okay, so this is when we can guarantee that we always have a solution even before we see the vector B. Okay, so that is corresponding to like this case. So even though we see like a simple example, this one is corresponding to the case where the span of the so here how many vectors do we have in this by viewing it as a vector equation? So we have 2 vectors, right? And what are these 2 vectors? It is 1, 2. So that is coming from these 2 coefficients, right? And then what was the other vectors? What was the other vector is 2, 1, right? So that came from this one and this one, right? And then let's consider this span of these 2 vectors. And now, in which dimensional space are these 2 vectors living? So these 2 vectors exist in 2-dimensional space, not in the 3-dimensional space, right? So in this case, so we have V1 or A1 here, which is our, let's see, 1, 2. And this one is A2, which is our second vector of 2, 1, right? And then let's consider the span of them. So if the linear combination coefficient was 1, 1, and then this one will be the point, and then you can now stretch out or how to obtain. You can now know how to obtain the span of these 2 vectors, right? So basically, the span of these 2 vectors will be the entire 2-dimensional space, right? So in this case, let's consider any vector B that we are given here as, for example, 1, -2, or -1 and 1, and so on. All these vectors should be inside of our span of these 2 given vectors on the left-hand side, right? So in this case, we can always guarantee that the solution always exists, right? Regardless of any vector, any given vector B. Okay. Okay. So this theorem is telling us the 4 different situations that satisfies or that correspond to this case where we can guarantee that we have a solution regardless of any vector, any given vector b. So let's look at the second one. Each b vector, or this one is like any vector b, okay, in this Rm, when M is m by n matrix. So if we had maybe 3 by 5 matrix, okay, so in this case, yeah, A is the coefficient matrix. So A is the coefficient matrix. So let's just consider all the linear combination coefficient on the left hand side. So for example, x1, 2x2 plus x3 equals 1, and 2x1, x2 plus 3x3 equals maybe negative 1. So in this case, we can think about the matrix by just collecting all the coefficients, not the augmented matrix. Okay, so in that case, it will be this matrix, right? By just collecting all these coefficients. Okay, so this one, let's call this matrix as A. Okay. Okay. So in this case, any vector B is a linear combination of the columns of an A, which means in this coefficient matrix, what is the column vectors or the ingredient vector to form the linear combination? Okay, so these vectors will be the columns in our matrix A, right? So the item B is saying that any vector B in this two-dimensional space So in this case, the matrix is 2 by 3, right? Because we have 2 equations and 3 unknowns, right? And then it is, yeah, in this case, B is like 1, negative 1. And this vector is, of course, living in two-dimensional vector space, right? And then, yeah, so this one is m times n, right? So because A is m by n matrix, and so B, so we should consider B as a vector in the Rm, right? Or R2 in this case. And this one, any vector B, is a linear combination of the columns of an A, right? So it means for any vector B, it is always represented as a linear combination of the columns of an A, or these given 3 vectors, okay? So these are column vectors in this matrix A. And then this one is actually equivalent to the third item. So the third item is saying that the columns of an A spans Rm, okay? So that means span of A1, A2, A3 is actually the same as the entire universe of our m-dimensional space. Okay, so in this case, what does that mean? The span of these 3 vectors are actually the same as the entire universe of R2. Okay, so this is when we can guarantee the existence of solution regardless of an any B, right? So the item B and item C are equivalent, and we can easily understand that, right? Okay, and then now let's think about this, the last item of B, and when is this condition, when is this case true, okay? So we can understand this by seeing the pivot position in our matrix A. Okay? So the last condition is nothing but what we've already learned. So let's imagine our augmented matrix And then if we see all zeros except for non-zero entries on the last column, this is when we have no solution at all, right? And then now we want to be able to avoid this situation in any cases or in any given B vector. Okay, so this is the situation. And then in this case, let's just consider this part. Regardless of the given vector B, let's just consider this matrix A, which contains only the coefficient, not the B values. Okay, so in this case, if we do the row reduction on this coefficient matrix in order to change it into the echelon form, okay, and in that case, if A, in the rows of an A, if in each row of this matrix A, if we can find the pivot in this matrix A, and then that is when we can guarantee we have always solution regardless of the vector B. Okay, so let me give an example. So it's a little bit tricky. So this is the example shown in the next chapter, but let's just consider this example. So in this case, what would be our augmented matrix? So it is a kind of special linear system where we have all zeros in the B values, and then this one will be our so this one will be our augmented matrix, right? And then let's try to do the row reduction, okay? And then we will obtain this, and then obtain this, okay? And then this one will be our echelon form, right? And then we can further change it into this reduced echelon form. But yeah, we don't need to go all the way to the reduced echelon form, but let's just think about this echelon form, which will reveal the position of the pivots. Okay, so here, where is the pivots in our augmented matrix? We see these two pivots, right? And then let's consider another case where we have the exact same coefficient, okay, but different B values. So in this example, we see 3, 5, -4, and -3, -2, and 4, and so on. And this part is exactly the same as this part. Okay. So the new example we see here is the same as the previous example, except for the B part, right? And then let's imagine the row reduction on this augmented matrix. So we will have this augmented matrix, right? And then we will have this augmented matrix, or reduced. So we will have this echelon form of a matrix, or reduced echelon form of a matrix. But let's imagine the detailed step or individual steps of this row reduction when trying to make this as an echelon form. So we will first focus on this element, and then we will remove these two values, right? And then suppose these guys became 0, and then we will obtain this part, and then if this one is non-zero, and then we will remove this guy, right? So this is how we do the row reduction, right? And then up to this point, or while changing it into echelon form, let's consider this part. So this part actually just follows so they just follow this row reduction, but they do not just determine, or they do not change or influence our row reduction process. So what I mean is that, so in this example, what kind of row reductions do we use in this case? So we will just multiply it by 1 and then add it to the second equation, right? And then suppose this guy was 1 and 2, and then this guy will be just added accordingly, like as 3, right? And then we will do, we will cancel out or make this one as 0 by just multiplying it by 2 and subtracting it from the last equation. So this is the detailed row reduction steps, right? So in this process of multiplying by 1 and adding it to the second one and then multiplying it by 2 and then subtracting it from the third one. So in this row reduction, these values will not influence this row reduction itself. So depending on different values that we are given on the last column, so they do not influence how much we should multiply and whether we add or subtract it to the other equations, right? So in that sense, they will just follow these row reduction steps, okay? So the point here is that if we are given a different values on the last column, they will just follow and they will not influence the row reduction result in this echelon form, or at least on the first part of matrix of A, okay? Okay, so if we had maybe 1, 2, and 3, okay, and then if we do the row reduction on this new augmented matrix, and then the resulting matrix will still be the having the exactly same part on the A part, okay, 3 and 5 and negative 4 and 0, 3 and 0 and 0, 0, 0, okay, and then only the last column will change, okay, because they do not influence the row reduction and how we do this row reduction exactly, right? So okay, so so my point is that if you do the row reduction and then this A part will not change at all regardless of this B part, okay? So they will just follow. So in this case, if the original B column or this last column was 1, 2, 3, and then of course the last column will change, right? But these 3 columns will not change, right? So so this is the point in this theorem of for the item 4. So as I mentioned, when imagining the row reduction given this B part, and then let's consider this part as the matrix A, okay, and this A part is containing our coefficient values on the left hand side, okay. So even if this value will change, even if this part changes, let's consider it's a row reduction form as maybe U, okay. So this part, so if this was maybe 1, 2, 3, and if this was maybe 3, 1, maybe 5, okay, regardless of any given vector B in this last column, the resulting echelon form of this matrix A will remain the same, okay. Okay, so so that means, so if you do the row reduction on this matrix A, okay, just excluding this part, okay. So let's imagine the row reduction only on this coefficient part, okay, and then you will obtain the exact same echelon form that we see in this part, okay. So if you understood this point, and then we can now see the really important characteristic in this row reduction. So the point is that the pivot position will not change, at least in this A part, okay. So suppose this matrix A was converted into an echelon form, okay, and that echelon form was, so this guy is corresponding to this, and this guy is corresponding to this B part, and then suppose, so we had this echelon form, and then in our echelon form we had a pivot positions as here and maybe here and here, okay. So this is, yeah, this is the case that we consider in this case. So in this case, pivot is found in the first, second, and the third, the fourth columns, but at the same time, each row, okay, so each row had a pivot, right, on the in the corresponding part of the variables. So every row or every equation, okay, every equation has the pivot, yeah, pivot whose position is corresponding to the variable, okay. So again, in this case, the pivots are existing. I mean, the pivots in every row is corresponding to our variable part, okay. So in this case, we are removing the possibility of having the pivot on the last column, right? So in this case, regardless of whatever vectors that we start on the right hand side, okay, they cannot be the pivot in our echelon form, okay. So that is the point. So if you do some exercise with some examples, and then you will see, you will easily see this kind of point. But again, let me summarize the point here. So if A is given and A is fixed, okay, and then regardless of this B part, okay, the echelon form, at least corresponding to this A part, will remain the same, okay, and in this same in this same echelon form, if the echelon form is the same, and then the pivot position will be the same, right? Again, the echelon form is the same, and then the pivot position will be the same, and then in that case, if such a pivot positions in every row is actually corresponding to all the variables, okay, in that case we are completely excluding or we are making it impossible, okay, to have a pivot on the last column, because we have a 3 row and thus we can have 3 pivots, right? And then 3 pivots are already found in our variable part, or except for up to the up to this column, right? So that means all the pivots are belonging to our variables, but not on the B part, and thus we don't see this kind of row at all, okay? So it is it's first time to explain this theorem, but it is always difficult to explain this. But But anyways, that is the point of this item D in this case. So A has a pivot position in every row, and A, what is A? So A is this coefficient part, okay? Coefficient part has the pivot, okay? that A part contains the pivot for every row or all the rows. Okay. Okay, so let's look at this example again, which is our 2x2 case. So there was a first case and the second case. So the first case, in this first case, depending on the values that we are given on the B part, sometimes it had a solution or sometimes it didn't have a solution, right? And what about the second part? We had a coefficient of 1, 2, 1 and 2 and 2 and 1. And in this case, we kind of understood that regardless of any given vector B on the right hand side, we always guarantee that we have a solution, right? So let's understand these two cases in terms of these pivot positions of the coefficient matrix. Okay, so let's look at this example. 1, 2. So this one will be our augmented matrix in this simple two equations with the two unknowns or two variables, right? So in this case, let's do the row reduction, okay? But I will just set these B values as a kind of an unknown, or I will just ignore them at this point, right? So in this case, the row reduction will be corresponding to like, we multiply it by 2 and then subtract it from the second equation, right? And then 1, 2, and x, it will not change at all, right? But what about the second equation? We will see 0 and 0 here, right? And then, so let's think about this as a star. And then this value will be x minus 2 star, right? But, okay. Star minus 2x. Great, So, even though we can compute this value in this manner, but we don't need to care about it, right? And then in this case, let's focus on our augmented matrix and the pivot position. And where is our pivot position? So pivot is definitely found here in the first row. And what about the second row? In the second row, there are two cases in terms of a pivot positions. But in this part of this coefficient matrix, right? In this coefficient matrix, in every row, it failed to have a pivot in every row, right? Because in A part, we have a pivot here in the first row, but in the second row, it didn't have a pivot, right? And thus, it actually makes it possible to have a pivot on the last column, right? So, if it was maybe 3 and 6, and then this one will be 0, and then this is a kind of a fortunate case where we have a solution. But we want to consider the situation where we have always the solution, regardless of any vector B on the right hand side. So if it was like instead of a 3, 6, if we had maybe 3, 7, in that case, we will have the pivot in this case, right, as 1, right? So in this case, we find the pivot here on the last column, and thus we have no solution in this case, right? Okay, so this is the case not corresponding to this theorem, right? Because we want to consider the case where we can always guarantee the solution regardless of any B. And then, even though it was simple, let's consider the second case, okay, this case, where we understood that we can guarantee that we always have a solution. In this case, 1, 2, 2, 1, okay, 1, 2, 2, 1, and maybe, this augmented matrix. And then, yeah, we will do the same thing, multiply by 2 and then subtract it from the the second column, and then 0 and what? -3, right? And then, yeah. So this one will be our echelon form, right? And in this case, where is our pivot? Pivot is here and pivot is here, right? So those two pivots are determined regardless of any values on the right hand side, right? So in this case, in every row, we have a pivot in this coefficient part, or the matrix A. So in this case, regardless of any values of this X mark or the stars, okay, we can guarantee, we can guarantee that we don't see this kind of column, this kind of rows, right? And thus, we can always guarantee that we have a solution. Okay. Okay, so that is the main point of this. Probably the most difficult part among these 4 entries. Yeah. So the last entry was about this. Yeah, this point. Any questions so far? Okay, then let me give an let me think about some other examples. So suppose we have 3 equations and 2 unknowns. In this case, we will have this augmented matrix, right? And then the coefficient part will be this part, right? So in this case, can we make, or can we think about the case where we guarantee, we always guarantee the solution regardless of any vector b here. So let's think about the possible pivot positions, okay? Okay, so pivots can be here and here, right? And then we used 2 variables. So in this case, it's corresponding to x1 and x2, and then this one is corresponding to the part of b, right? And then pivots can exist, up to pivots can pivots exist at most only once per column and per row. So that means, suppose we found the pivot here, and then can we find the pivot in the these are lower entries? It is not possible, right? And thus we move on to this sum matrix, right? This sum matrix. So that's how we do the row operation, right? And then suppose we found the pivot here, right? And then can we find the pivot here again? We cannot find it, right? And then we used these 2 variables as a pivot positions, right? And in that case, there is no way to place the pivot in the last row by using these 2 variable columns, right? So in this case, it is not possible that we can guarantee we have always the solution, okay? And then let's think about it in the from the perspective of a span. So from the vector equation perspective, how many vectors do we have? So we have a vector, we have these 2 vectors, and then we are given these third vector, which is our b vector, and these 2 vectors, and let's think about the span of them, right? And then these 2 vectors are living in the 3-dimensional space, and we only have the 2 vectors, right? And then the span of these 2 vectors will be just a thin plane. So there is no way to cover the entire 2-dimensional space by using these 2 vectors, or the span. By spanning these 2 vectors, we cannot cover the entire 3-dimensional space, right? So that's why we cannot guarantee that we have a solution all the time. Because if the B, whether we have a solution or not, is actually dependent on whether our vector B is falling inside of our span of these two vectors, or it is still possible that this vector B is placed outside of the span of these two vectors, right? Okay, and then, let me think about some other cases where we have two equations and three unknowns. So we now have a coefficient matrix here, and then the pivot positions can be like somewhere around here, okay, corresponding to the first variable and the third variable, but not on the second variable, right? So in this case, the entire space is two-dimensional space, right? And then how many vectors are we given? We are given these three vectors, right? So we are given three vectors, okay, three vectors, but in the two-dimensional space. So something like this. So we have one vector and the second vector, and then maybe the third vector. And then let's consider the linear combination of these three vectors, okay? And then, v1 and v2 and v3. And then let's just ignore this v3 at first. And so let's just set the linear combination coefficient as 0. And then let's just think about the span of these v1 and v2. And then it will already cover the entire two-dimensional space, right? And thus, by using these, only the two vectors, and we can already cover the entire space of our two-dimensional space. So in that case, we can guarantee the solution will always exist. Okay. Yeah, but in this case, this figure is a little bit wrong. Okay, this figure, it is a little bit wrong because in this case, the second variable didn't have a pivot. Okay, didn't have a pivot, right? So in this case, let me give an example. So 1, 2, 3, okay, corresponding to these three values. And then, suppose, let's consider the case where we have a pivot here and here, but not on the second column. So in that case, let's consider this matrix. And then, if we do the row reduction on this matrix, and then 1, 2, 3, x, and then this one is star and 2, and it's 0 and what? We have 0 here as well, and then 1 here, right? And some star prime, okay, which is our new constant, which we do not care, okay? In this case, we have a pivot here and here, right? So, which is corresponding to this case, okay? And then in this case, suppose, so let's look at the actual vectors that we have. So we have 1, 2, and 2, 4, and 3, 7, okay? So in this case, 1, 2 is here, and where is 2, 4? Where is 2, 4? It is actually along the line of the first vector, right? So this one will be our second vector. So in that case, even if we have two vectors so far, the first vector v1 and v2, in that case, is the span of v1 and v2 the same as the entire space of an R2? Is it true or not? It is not true because, let's just try to parallelogram by using these two vectors, V1 and V2, but they are actually having the same direction. Okay, and then maybe V1 times 1 and V2 times 1. Okay, so in this case, this vector and this vector, and then adding them together, we will just obtain this vector. Okay, so this still remains along this line, yeah, that has the same direction as V1 and V2, right? So in this case, span over V1 and V2 will still be a thin line which doesn't cover or which doesn't span the entire two-dimensional space. Okay, but fortunately we have a third vector that has the pivot position, right? So the third vector has actually a pivot position here, right? So in this case, 3,7 is somewhere like 3, yeah. So this was 3,6, but we have a 3,7 here, and so now our third vector is something like this, right? So even though these two vectors have a kind of similar directions, they are not exactly the same. So they basically have a different direction. And then if we draw all the possible parallelogram by using these two vectors, and then yeah, we can cover the entire two-dimensional space, right? Okay, so in this case, if we see the pivot here, so back to the theorem that we studied, this is the case where we can guarantee that we always have a solution, regardless of an NAB value here. Okay, but what about this? So even though we have two equations and 3 unknowns that has more variables than the equations, let's think about this case where we have 6 here. Okay, so let me just have a 6 here. Okay, so in this case, we are given 3 vectors, and then what about their augmented matrix, the pivot positions? It will be 1, 2, 3, and x, and it will be 0, 0, 0, and star prime, right? And then the pivot is found here, right? But we don't see the pivot on the second row corresponding to the coefficient part, right? So in this case, we cannot guarantee that we always have a solution. So depending on these values, so for example, if it was like 6, if it was like 6 and 12, and then it is the case where we have a solution. But if it was 6 and maybe 5, right? In that case, that is not inside of the span of these 3 vectors. But these 3 vectors are actually having the same direction, right? So they work just as a single vector from the perspective of a span, right? Even though we see the 3 vectors, they have all the same direction, and thus, so it will be just the same as the span of just a single vector, okay? So this is corresponding to this case, and then in that case, we don't see the pivot. We don't have the pivot on the second row in this part, right? So that way, we cannot guarantee that we always have a solution. Okay. Okay, and then let's stop here, and then let's continue next time for the other parts in this chapter. Okay, thank you very much.
표기를 이런 식으로 해도 돼요. 스팬 해놓고 이 벡터
네.
이렇게 그냥 바로 써도 돼요.
그 끝나기 전에
네.
1,2, 2,4, 3,7에 대해서
네.
True or False 질문하신 거 약간 그 부분 영어 해석을 잘못해가지고 제대로 못 들었는데 다시 한번 설명해 주실 수 있을까요?
1, 2, 3, 2, 4, 7 뭐 이런 거요?
네.
네. 네. 요거? 아니면
네,
어디?
그 부분에서
네.
그 true, false 앞에 그 문장 질문을 해석을 쓴거
아,
못하고
내가 뭐라 그랬죠? 기억이 안 나네. 어떤 거였더라? 바로 직전에 얘기했었네요, 내가.
네.
아니 그냥 선생님한테 분야 관심 있어요.
글쎄요. 가만 있어보자. 그러니까 이게 일단은 이게 2차원 스페이스면
네.
네, 좀 직관적으로 보면 이게 두 개의 벡터가 있으면 이 2차원 벡터를 fully span을 해요. 그러니까 전체를 다 뒤덮을 수가 있거든요.
네.
근데 실제로 그러니까 벡터 두 개 혹은 그 이상이 있을 때는 이 전체 스페이스를 다 스팬한다라고 일반적으로 볼 수도 있지만 일반적으로 그런 게 이제 일반적인 좀 패턴이지만 실제로 그 세 개 벡터가 그러니까 실제 2디멘전al 스페이스에서 벡터 개수가 이 디멘전의 개수보다 더 많이 주어졌어도 이런 경우 세 개 벡터가 주어졌을 때 이런 경우에 실제로 얘네들이 조금은 뭔가 제 역할을 다 하고 있느냐. 그러니까 첫 번째 벡터, 두 번째 벡터, 세 번째 벡터. 그러니까 첫 번째 벡터에서 두 번째 벡터를 이렇게 늘어날 때 이게 다른 방향이어야지 이게 스팬을 늘려주는데 이거는 지금 다 같은 방향이잖아요.
네.
그러니까 이거 벡터 개수는 많아도 얘네들이 하는 역할이 첫 번째 벡터에 비해서 뭔가 더 이렇게 좀 추가적인 어떤 스팬을 넓혀주지를 못한다는 이야기가 되거든요. 네, 그래서 이런 경우에는 이제 그 에슐론 폼으로 만들어서 피벗 포지션을 보면 여기에 있고 또 이 아래에는 하나도 없게 돼요. 네, 그러다 보니까 여기에 뭔가 난제로가 들어가면 이때는 솔루션이 없을 수도 있는 거죠. 그 말은 이거의 세 개에 대한 어떤 벡터의 스팬은 결국은 이 전체 스페이스 중에서 이 라인 여전히 그 아주 얇은 이 라인일 뿐이에요. 그러니까 벡터 B가 여기에 쏙 들어오면 그때는 해가 있는데 이 바깥으로 삐져나가면 해가 없을 거라는 거죠.
그때 아까 전에 여기 7이라 쓰시고
네.
그 명제돼서 false라고 하셨던 그런 문제 의도가 그 스팬이 넓어지니까
네, 맞아요.
그런 뉘앙스였겠죠?
네, 그렇죠. 그렇죠. 여기가 세븐이면 첫 번째, 두 번째는 그냥 한 라인으로 머물러 있었는데 스팬이
네.
그러니까 세 번째 벡터를 실제로 추가하면 실제로 요 어떤 벡터들의 스팬이
네.
이제는 전체 2디멘전을 다 뒤덮을 수가 있고 그 말은 여기에 피벗이 이렇게 나타나는 경우가 돼서 이 경우는 이제 그 항상 해가 이렇게 존재한다라고 얘기할 수 있죠.
감사합니다.
만약 그럼 이게 여기서 6이었을 경우에는 스팬을 V1, V2, V3 다 넣었을 때 R1으로 써야 되는 거예요? 지금 여기는 이렇게 나와서
네네네.
되게 헷갈렸거든요.
네네, 그거는요 그냥 R1이라고 안 쓰고요. 그냥 뭐 별다로 쓰는 건 없어요. 그러니까 R1은 뭐냐면 R1이라고 하는 거는 이거는 벡터 자체가 1차원에 살고 있는 벡터여야 돼요. 그러니까 그 스케일러라는 뜻이죠.
그러니까 공간 안에 존재한다는 거지. 이게 해 자체가 뭐 직선이면 R1.
네, 그렇지는 않아요. 네. 직선이라 하더라도 이 직선의 포인트들은 지금 일단 2차원상에 있는 이 포인트들이니까 얘네들이 이제 R2, 그러니까 전체 집합으로 보면 이 2디멘전에 존재하는 애들이고.
네, 스팬이 이거랑 같다고는 할 수가
그렇죠.
없는
스팬은 그냥 여기에 그냥 포함이 쏙 되는 거지 이거랑 같지는 않은 거로 그냥 이야기를 해야 될 거예요.
배운 내용 제대로 이해했나?
네.
오늘 배운 게 AX는 B 에슐론 폼을 이렇게 A랑 B 섹터로 나눴을 때
네.
이제 B 값에 상관없이 해를 무조건 가지는지 아니는지를
네, 맞아요. 네.
벡터 관점에서도 보고 에슐론 폼 관점에서도
맞아요. 네. 정확히 그거예요.
네, 에슐론 폼은 확실히 알겠는데 벡터 관점이 혹시
네, 네.
여기 B의 이제 로우 수가 이제 차원이잖아요. 벡터에서 차원.
네, 네.
그래서 그 차원을 이제 결과값을 그 차원의 어떤 임의의 값이 나올 테니까 B 값이 그러면 이제 그 벡터는 적어도 그 차원 개수 이상 있어야 그거 전체 부분이 될 수 있다.
네, 뭐 그런 시스템이에요.
아,
네, 맞아요. 그러니까 그런 얘기를 좀 더 다음 시간에 아마 하겠지만 일단 전체 스페이스가 그러니까 이퀘이션 개수가 일단 우리의 어떤 그 디멘전, 그러니까 전체 스페이스의 디멘전을 결정해요.
네.
이퀘이션이 한 5개 있다. 그럼 일단은 이 벡터 이퀘이션 측면으로 볼 때 이제 주어진 어떤 스팬에 사용된 주어진 벡터나 아니면 이 B 파트에 이 B에 주어지는 벡터나 모두 다 5차원에 있는 지금 벡터를
네.
우리가 생각하는 거예요.
네.
근데 5차원에서 뭔가 벡터가 3개밖에 안 주어져 있어요.
네.
그러면 이게 기본적으로는 3개의 벡터만을 가지고 이 5차원 전체를 다 뒤덮을 수는 없게 돼요.
그래서 이제 이게 그런 경우에는 이게 안 되는 거고.
그렇죠. 네, 그게 그리고 왜 안 되냐? 이 정도거든요. 그러니까 3차원인데 지금.
네.
그러니까 얘네들이 살고 있는 스페이스는 3차원인데 지금 주어진 벡터는 2개밖에 안 되잖아요.
네.
그러니까 3차원 스페이스에서 이 두 개만의 벡터를 가지고 스팬을 아무리 해봐야
평면밖에.
평면밖에 안 되는 거예요. 그렇기 때문에 그 경우는 전체를 뒤덮을 수가 없게 되고, 그거는 또 지금 아까 이야기한 것처럼 피벗 포지션의 관점에서 보면 이 로우는 3개인데,
네.
그래서 로우마다 다 피벗을 우리가 채워줘야 되는데, 이 베리어블들을 가지고.
네.
근데 베리어블은 2개밖에 없으니까 끽해봐야 여기나 뭐 예를 들면 뭐 여기 여기 나올 수가 있나? 이건 이렇게 나올 수가 없는데, 이거는
네.
네. 하여튼 그래서 이제 이게 2개만의 베리어블로 이제 3개 로우의 피벗을 채워줄 수가 없기 때문에 이거는 그래서 해가 항상 존재하지는 않는다. 그러니까 B를 봐야 된다 이거예요.
죄송한 질문 하나만 더
네.
드려도 돼요? 이제 그러면 이제 2개 이런 A를 이루고 있을 때는
네.
피벗이 이제 이렇게 2개가 존재할 수 있고, 그럼
그렇죠.
항상 해가 있을 수
그렇죠.
있는데,
네.
이제 이게 피벗이 안 될 수 있는 경우도 있잖아요. 삭제하다가.
네.
그런 경우는 벡터 관점에서 보면 평행하다, 둘이 평행하다는
맞아요.
말이에요.
네. 맞아요. 그러니까 이게 지금 이런 경우잖아요. 그래서 아까 1, 2, 2, 4 여기에서 그러니까 이퀘이션이 두 번째가 주어졌지만 이제 여기에 피벗이 생겼고, 그 다음엔 여기에 좀 생기길 원했는데 이게 같이 지워졌잖아요.
네.
그러니까 그거는 그 방향, 이 벡터 방향이 같았기 때문에, 이거 2개의 벡터 방향이 같았기 때문에 그렇고, 요 놈이 그래서 0이 되니까 여기 피벗이 안 나온 거죠.
에슐론 폼 만드는 과정에서 만약에 이제 두 벡터가 평행했으면 이제 그 중에 피벗이 나올
네.
수가 없다.
네. 근데 또 이런 경우가 있어요. 이게 좀 뭐 이런 예제까지 좀 이게 이런 경우가 있어요. 그러니까 이 3차원 공간에서
네.
이렇게 아까 그 3차원 그림이 어디 있나? 네, 여기서 보면
네.
이제 V1이 예를 들면 1, 2, 3이에요.
네.
그 다음에 V2는 이제 뭐 예를 들면 1, 3, 5예요.
네.
그럼 1, 2, 3과 1, 3, 5는 분명히 다른
네.
방향에 있어요.
네.
그래서 이 2개로는 이렇게 평면을 스팬을 하는데, 예를 들면 V3가
평면하네.
네, 2, 5, 그러니까 2, 5, 8 이 말은 지금 요거랑 요걸 내가 그냥 단순히 더한 거예요. 즉 1 곱하기 V2, 1 곱하기 V1, 1 곱하기 V2라는 리니어 컨비네이션, 이렇게 덧셈을 해갖고 만들어진 요 벡터가 우리의 V3라고 한다면,
네.
이 벡터는 실제로 이 V1과 V2가 스팬하는 그 평면 안에 지금 들어와 있는 애예요. 그러면 아까 얘기했던 것처럼 이 V3가 추가가 되면서 이 V1과 V2에 이렇게 스팬되는 그 평면의 높이를 조금씩 올려주면서 이 전체 3차원을 다 뒤덮어 주기를 바랬는데,
네.
V3가 실제로 요 안에 쏙 들어가 있기 때문에 이 높이를 올려주거나 내려주는 역할을 못 하는 거예요.
저 경우에도 에슐론 폼 만들다 보면 피벗이 중간에
네,
하나
맞아요.
사라지긴.
네, 그래서 1, 2, 3, 그 다음엔 1, 3, 5, 그 다음에 2, 5, 8에다가 뭐 이렇게 하잖아요.
네.
그러면 이 경우에 에슐론 4를 만들면 여기 피벗 생기고 여기 0, 0 되고요.
네.
그 다음에 여기 피벗 생기고 여기 0 되는데,
마지막에
요 놈이 0이 돼요.
그래서 피벗이 안
네.
되고.
그래서 맞아요. 그래서 피벗이 이제 여기 그런데 여기는 없는, 이렇게 돼요. 네, 이렇게 되면 이제 또 3차원을 다 뒤덮지 못하는 경우가 생겨요.
네. 감사합니다.
수고했어요. 네.